Thank you so much, Lamek. Let me go back on some of the issues with the current state of the art that you have highlighted. I will present some promising ways in which recent developments in AI and machine learning can help us solve those issues. I work for Annie at the EPFL Intelligent Global Health Group, where our close relation with the Machine Learning and Optimization Lab allows us to apply the latest technological advances in our work. Let's dive right in. Despite knowing all the issues highlighted by Lamek, people and organizations still regularly aggregate records from tens or even hundreds of institutions into centralized datasets. And they do it because it is worth it. The statistical power gained from the aggregation of several data sources can really outweigh the negatives. As an example, the Infectious Diseases Data Observatory created a centralized Ebola data platform from 19 treatment centers active in 3 countries during the 2014 to 2015 West African Ebola epidemic. To do this, they had to engage in lengthy negotiations with multiple parties to create a common agreement and to treat the data to make it interoperable across centers, institutions, and boundaries. This whole process took 4 years, such that the platform opened for data access applications in late 2019. Thankfully, there are ways to achieve the same result without ever copying any data. This approach is called collaborative learning. The only copy of the data and control over it remain at the site of collection, thus eliminating the need for lengthy and complicated negotiations, and hence things could move much faster. In fact, I believe that a world in which statistical models can be trained on an aggregate dataset during an epidemic is possible within the next 5 years. There are 2 prominent paradigms of collaborative learning which differ in the shape of the communication network. In federated learning, individual participants communicate bilaterally with a central server. These participants are any entities that hold data. They can be institutions such as hospitals or individual mobile devices, etc. In contrast, decentralized learning methods rely on each participant sending messages around to their neighbors, or in other words, to a subset of the other participants. The definition of a participant is the same as for federated learning. Importantly, it is possible to learn exactly the same model as with a centralized data set, all the while ensuring that individual messages do not compromise any individual datum points, though that is not trivial, admittedly. In fact, any gradient-based method can be implemented in a federated and/or decentralized way. This means that collaborative learning works for simple models, such as linear regression and logistic classification, as well as terribly complicated, deep convolutional neural networks. With decentralized learning, or federated learning with a trusted server, any of the agents contributing data can train whichever model they like. Thus, the benefits of data collection are more directly available to those who collected it in the first place. In addition, ownership and control remain with the original data collector, such that they can decide what the data is used for. Several frameworks have been created to enable federated learning, some of which are specifically aimed at medical applications. First, there are fairly general federated learning libraries that extend some of the most popular machine learning frameworks, such as TensorFlow Federated for TensorFlow and PySift by OpenMind, which is compatible with both PyTorch and Keras. There are also some more specialized frameworks. For example, XANET is a backend for privacy-preserving cross-device federated learning that supports working in browsers and mobile apps, while Fate markets itself as an industrial-grade federated learning framework with a bigger focus on settings where the participants are, say, servers rather than mobile phones. Additionally, some frameworks have been developed specifically for medical applications. NVIDIA developed an AI framework for healthcare, which now features federated learning. As a side note, it is the only closed source project on this slide. NVIDIA also collaborated with several universities to develop MONAI for healthcare imaging, which also recently gained some federated learning capabilities. Finally, at IGH, we are developing an interactive machine learning platform for healthcare called ALGE. Support for federated and decentralized learning is planned for later stages of the project. However, there are some issues we have yet to address. For instance, one of the most labor-intensive tasks when creating a centralized database is to make the data interoperable. It might even happen that the aggregated data is not representative because data from specific hospitals is left out due to systematic interoperability issues. In the collaborative setting, it is now the responsibility of individual data collectors to ensure that they collect data in a way that is interoperable, e.g. by complying with a certain standard. Of course, the data collectors need incentives for exerting that effort. Thankfully, collaborative learning inherently incentivizes interoperable data collection, at least to some extent, since collecting data in an interoperable fashion allows them to leverage other people's data. So that sounds good. But what about the issue of data poisoning mentioned by Lamek earlier, where lazy or even malicious agents participate without having exerted any data collection effort? Well, here, there are some federated learning and decentralized methods that have strong Byzantine robustness guarantees. Beyond that, there are also model personalization methods, which we shall discuss next. Model personalization provides incentives for the collection of high-quality data, thus also rewarding interoperable data collection and discouraging data poisoning. The underlying principle behind model personalization is to assume that each participant samples data points from a different distribution. So there are as many models to learn as there are participants. To visualize this, let's assume that the participants are hospitals dispersed in the world. Differences between the data distributions from which they sample, in other words, the distribution of people that come to their hospital, are represented through color. As more and more hospitals join the federated or decentralized training network, we start to see some patterns emerge. In this example, variations seem to be largely driven by geographical location. However, this is not the only confounding variable one could imagine. For instance, urban hospitals might see quite a different distribution of diseases as compared to neighboring rural hospitals. Given this, if I am one of the participants, how do I train the best model possible? Of course, I could just train a so-called local model by using only my own data. However, doing this, I run the risk of overfitting. If the number of samples at my disposal is insufficient, I might learn a model that doesn't actually work for new patients. If I collected the same number of samples again to train a different model, I might end up with two clearly distinct models. In other words, the model itself has a large variance. It's unreliable. On the other end of the spectrum, I could use all data available on the network to train what's called a global model. And in many cases, especially when training models with a very large number of parameters, this model already performs a lot better. For instance, convolutional neural networks for image analysis have quite many parameters. However, by including samples that are representative of an entirely different population, such as the green samples here, I risk introducing a bias that could make the resulting model perform suboptimally on new patients at my hospital. Model personalization methods seek to solve one issue without making too many concessions on the other. There are several approaches, some of which can be combined. The following is just a selection of a few methods, as we couldn't reasonably cover them all in this talk. Several model personalization approaches rely on clustering the participants. This can happen either before or during training. Another approach, called featureization, uses context information like the mean population density in the hospital's catchment area as model features alongside the patient-specific features, such as fever, temperature. There's also local fine-tuning, which consists of training a global model and subsequently fine-tuning it by completing a few training iterations on the local dataset. As a side note, there are also schemes where the global model is specifically optimized to provide a good starting point for local fine-tuning. And finally, we developed the weight erosion scheme at IGH this year, which uses distances between gradients to differentiate participants by their usefulness for the training task at hand, and does this during training. One of its main advantages, thus, lies in its relative parsimony with respect to complexity and communication traffic. Of course, it becomes clear that some methods, notably the clustering-based ones, but also weight erosion, provide a certain level of robustness to malicious actors, such as the yellow and orange participants here, who have failed to collect any data and just send random messages to the network instead. This is also called Byzantine robustness. Additionally, these methods can be useful in detecting outliers that would be expected to belong to one cluster, but end up in a different cluster or even on their own, because of some systematic error in the data collection process. Depending on the specific approach, model personalization can also readily be used to provide further incentives for good data collection. For example, participants could be rewarded more if they end up in the same cluster. So, where does all that leave us? We've seen that collaborative learning, especially when used in conjunction with model personalization, can help solve many of the issues introduced by Lamek. Here are some of the next research directions that I see on the AI side of AI for global health. For us at IGH specifically, it would be interesting to apply weight erosion to a few benchmarks, including medical imaging, so as to compare it to other methods in the literature. Further on the topic of model personalization, some of the main approaches to model personalization still need to be implemented in the existing collaborative learning frameworks. Another topic that I am currently working on at IGH is that of equipping machine learning models, or their predictions, with confidence measures. This could be something like a 95% confidence interval. There is some literature on this topic, but a few open questions remain, especially in a collaborative learning setting, and even more so in the presence of model personalization, because personalization introduces a sampling bias. Finally, since I have talked so much about the current and potential use of artificial intelligence for global health, I'd like to present you with an alternative interpretation of this phrase. AI affects global health directly through the opportunities it creates, but also indirectly through how it changes people's behavior on a global scale. Thus, AI for global health also means making sure that the way artificial intelligences are designed is aligned with global health priorities. One major way in which it is arguably not aligned at present can be found in how the content recommendation algorithms of major social media platforms have contributed to the spread of dangerous misinformation on vaccines, on SARS-CoV-2, on bleach, and whatnot. because they had learned that conspiracy theories do a fantastic job of creating user engagement and of maximizing watch time. The impact of these AIs on global health, for example in the shape of measles and COVID-19 cases, merits further investigation, especially so since most of the research to date has been focused on high-income countries. Thank you so much. I will now leave the floor to Valérie and Tristan, who will discuss the work they have done to quantify and reduce the considerable environmental footprint of AI.